Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber Physical Systems, IISc. Today's talk is by Dr. Harshad Khadilkar, and he will be speaking on using machine learning for doing rather than knowing practical applications of RL in industry. Dr. Harshad is a senior scientist with TCS Research, a visiting associate professor with IIT Bombay, and an associate researcher with RBCDSAI IIT Madras. His research interest is in control and optimization of large distributed systems, especially in problems related to operation research. He holds a bachelor's degree from IIT Bombay and master's and PhD degrees from Massachusetts Institute of Technology. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on our future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may raise your hand and ask Dr. Harshad directly. Over to you, Dr. Harshad.
Thank you. So you can see my screen and see me and hear me, right?
Yeah.
Okay. Yeah. So thanks for the invitation, everybody. I think this is the first time I am attending this seminar series, so I'm not entirely certain how it goes, but generally what would be a good idea is if you have any questions, just unmute and ask yourself so that we can keep it as informal as possible. So I'll be talking today about using machine learning for doing in the sense of taking actions rather than knowing in the sense of doing some kind of prediction or forecasting or anomaly detection kind of task on a given system, right? So most of us will have seen, if we have worked with machine learning at all, applications in these areas where you generate what are called actionable insights, right? And these insights by themselves imply that they are actionable, which means they enable you to take actions, but they are not the actions themselves. Right, so some human being or some other system has to then decide, given an insight into your data or the operation of your system, this is something else has to decide what should be done about it. And today what I would like to talk about is a few algorithms and with real world case studies from our experience at TCS Research on how these actions can be computed automatically. And the way to link these to signals and systems, which is the area of interest of this seminar series, is to think of everything you observe about a system as a kind of signal. So think of it as a vector signal. If you're observing a system, say a dynamical system, then you can consider its position, velocity, angular velocity, etc. as signals that you want to control in some way so that the system enters what are called good states rather than bad states. And the question now is, what action should you take, or how should you manipulate the signals that you're observing to produce the right control actions? So that's going to be the theme of today's talk. So the agenda will be, first we'll talk about some interesting problems in distributed industrial systems. Distributed in the sense of it's not one dynamical system like a robot. It's going to be a bunch of different actors working together to produce some kind of output. So you can think of a manufacturing plant as a distributed industrial system where every robot or machine is doing its own job, but at the same time, its job and its output, its efficiency are dependent on what all the other machines and other actors on the manufacturing floor are doing. And the same thing works with supply chains, and the same thing works with this example on the screen now, which is actually a competition from called Flatland from a couple of years ago in Neurips, 2020, where the goal was to get these trains, which are kind of helpfully circled with these magenta colored circles and ellipses. So these trains are moving along these tracks, and your goal as a controller is to decide where each train should go. If there is a fork in the path, so for example, this train can go straight on or it can turn left and follow the other train. So these kind of decisions you have to take. You can also ask a train to halt somewhere to let other trains pass and so on, right? So this is a distributed system in the sense there are many different trains who have different origins and different destinations, and you are trying to control them in some way so that all of them get to their destination in the minimum average time. And I'm happy to report that 2 years ago, when we participated in this competition, we actually had the second best reinforcement learning based solution in that competition. The second thing I would like to talk about in today's talk is how can we use AI or machine learning driven algorithms for producing these automated control algorithms. So for those of you who are from operations research or related fields, you will immediately know that these kind of distributed vehicle problems have many heuristic based solutions, what are called multi-agent path planning solutions, right? So the question is, why should we use AI for doing these decisions when we already have pretty efficient heuristics? And what is it that AI buys us, right? And the third part of the talk will be about explaining 1 and 2 together through some applications and examples. Right. So we'll first take a look at some motivating examples of why AI-driven systems are required. Right. So this is an example from a large set of projects that we are doing in TCS research in the area of supply chain, especially in this example in the area of retail supply chain. Which means that you are not particularly looking at what's happening on the manufacturing side of products. You are looking at what happens when a retailer, a very large retailer like say Amazon or Reliance Fresh or DMart, when they take delivery in their regional distribution centers of maybe 100,000 or 1 lakh different product types, right? And they're all stocked in these very large regional distribution centers. From there, they are sent on to smaller distribution centers, maybe in specific cities, or in the case of large cities like Bangalore or Bombay, in specific neighborhoods. And then they are delivered to individual stores, or they could be delivered through an e-commerce warehouse directly to customer doorsteps. Right? So you have what are called omni-channel retailers. Omni-channel means the same set of products from the regional distribution centers are sent to or are shared between the physical brick and mortar part of the retailer, which is the stores, and the e-commerce part of the retailer, which is the houses. Okay, and the complexity here is in two different directions. One is in the variety of products that are passing through this supply chain, right? So you have 1 lakh plus products which are passing through here. And you can imagine that all of them will share space everywhere they go, right? So here they will be sharing shelf space. During delivery, they are sharing space on the truck and so on. Somebody has to physically pick them up. So they require some kind of labor inputs. They require some kind of prediction of what the demand will be in a specific store for a specific product and so on, right? So there is what I would call the product dimension complexity. The other complexity is in the direction of time. So as you move from left to right in this supply chain, you have faster and faster time scales. So on the leftmost side, you have contracts with vendors, which is the manufacturers, and these are set up months in advance by retailers, right? So you will deliver X quantity per week for the next 6 months. Is a type of contract you might set up with this manufacturer of, say, shampoos. Okay. From there, the regional distribution center probably restocks these local warehouses maybe once every week or once every couple of weeks. The local warehouses send products onto the stores perhaps once a day or a few times a week. And e-commerce deliveries, as you know, today happen within hours, right? So you can book something and expect to get it delivered on the same day. And the question is, how do you ensure this? Right. So as you get faster and faster time scales, you can think of them as faster and faster control loops in a plant. And as you can imagine, the slowest loop here is what causes the most instability in our plant. Okay, and so it's the hardest one to control. And then you have to imagine that all of these individual controllers, if you can think of them, sitting inside the store, sitting inside the warehouse, etc., have to decide what should be asked for from one level up the supply chain. So the store decides what to request from the warehouse decides what to request from the regional distribution center, and so on. And so some of the problems we have worked on here are, how do you manage all of the products coming in here? How do you distribute them on to other stores or warehouses, so which are called sorting center operations? Now, you have problems in the area of 3D bin packing, because these objects come, or products come as pallets, and so you have to pack them into larger bins for onward shipment. So how do you pack these bins to ensure maximum efficiency? How do you decide what should be replenished, what product should be replenished in what quantity on any given day, and so on. Okay, and so we'll come to a few more of these applications in a few minutes' time. But I just wanted to motivate this, that this is a complex dynamical system, if you want to think of it that way, which is producing a large range of signals in the form of inventory levels, demand forecasts, capacity constraints, and so on. And for which you have to compute control decisions, which are in a myriad different ways, correct? So you have decisions in the form of product replenishment quantities, you have decisions in the form of vehicle routes, you have decisions in the form of placement of boxes into bins, and so on. And if all of them work together well, only then you will get a highly efficient supply chain. And today's problems with delays with car deliveries, food deliveries, etc., because of supply chain issues, are essentially because of a lack of coordination between these different functions. And so our goal is, how do we make them work with each other rather than be optimized in silos. Right? So it's not necessary that these kind of concepts only apply to industrial systems. They can apply to what can be called social systems as well. And this is one of kind of interesting things that we did when we first went into lockdown in March and April 2020. Was we were all experiencing lockdowns at the district level, city level, etc. And there was a nagging sense that all of this was being done simply by gut feel. Right? I hope all of you agree that there was very little quantitative thinking happening in terms of when lockdowns happen, what is allowed, what isn't allowed, and so on. Right? And so we said, as an intellectual exercise, can we think about optimizing these lockdown decisions, thinking of the social signals that are coming from all over the country, and deciding quantitatively what is necessary to be done. Right? So what you're looking at here on the left-hand side is our understanding of how COVID progresses through a single person over the course of the disease. So you have S being a susceptible state, E being exposed to the virus. If you are exposed to the virus, there's an 80% chance you will show symptoms. So this is infected symptomatic, 20% chance that you are infected asymptomatic. And then if you're asymptomatic, you always recover. If you're symptomatic, on average, say you have 98% chance of recovery, and so on. Right? So this was our understanding of the disease back in early 2020. So we didn't have an arrow going back from recovered to susceptible again. Now, although now we know that you can catch COVID multiple times, but typically you will then only take the asymptomatic path. Right? So this was our disease model for individual people. And we said, let's look at districts in India. Okay, so there are about 700 districts in India, and they have these social connections between pairs of districts. So how strongly people move from one district to another and within the district, of course. Right? So you can have some kind of network flow models of how COVID can be carried given the number of infected people in a given district and the connectivity with neighboring districts. So you see that there's a catchment area around Bombay, another around Delhi, another around Kolkata, and another in this kind of Chennai-Bangalore nexus, right? And so you have strong connections in local catchment areas, but you also have strong connections between pairs of metros, and that makes sense. Okay, so if you wanted to decide what each of these districts should do every week, okay, we said let's look at how can we develop an AI-driven model to control these social signals to keep things balanced between healthcare costs and economic cost, because that was the key kind of trade-off that people were facing during the pandemic. Right? And we'll come back to how the solution was developed for this problem. So yeah, those were a couple of motivating examples. Before we go into the core part of the talk, are there any questions so far? Okay, so let's continue. So what I want to talk about is at an intuitive level, how we are thinking about AI-driven control or AI-driven optimization. If you think of control problems as in essence, an optimization problem where you're trying to minimize or maximize some kind of function of the states X, which we think of as the signal, and U, which is the action or the actuator decisions, right? So you're trying to find what is it, the U star, the action that maximizes a function f of the signal and the action itself, subject to a couple of standard types of constraints. So you have equality constraints, g of xu equal to 0, and you have inequality constraints of the form h of xu greater than or equal to 0. Typically, g of xu equal to 0 will be a dynamical system model which tells you how the system will evolve given x and u. But at this point, we are just looking at a static optimization problem. So there's no dynamics at this point. And h of x of u will be some kind of energy availability or cost or budget kind of constraints, right? So these kind of problems can be spatially quite large, spatially in the sense the dimension of x and the dimension of u, as well as the number of constraints of type G and type H can be very, very large. But people know of many optimization approaches now which can solve these problems no matter how large they are. So you have mixed integer linear programs in case these objectives and constraints are linear in nature. You have meta heuristics like genetic algorithms, simulated annealing, and so on. So there is a lot of different algorithms which can solve a static optimization problem. The real complexity comes in when we have what is called a sequential optimization problem.
Just a question here.
Yeah.
Ask a question.
Yes.
Yeah. So if you go back to the previous slide, this function has in it signal and the control. What about the parameters? Are there no parameters that you're supposed to learn, or that's implicit in the?
Yeah, so at this point, I'm not posing the learning problem. I'm just stating a basic optimization problem. So the function f will, of course, contain a lot of parameters. Yes.
Okay. All right. Thank you.
Yeah. But I'm assuming the parameters are fixed. What you're trying to find is the u star given any x. Right. So this f, for example, could be given by ax plus bu, to take the simplest possible example. So a and b in this case would be fixed, and you would just try to find the u star that maximizes ax plus b given an x.
This is like a state control model, right? X is the state and u is the.
Correct. Okay. All right. So the complexity, as you indicated just now, is not in a static optimization problem, but in what is called a sequential optimization problem, where you no longer have a single optimal u star for a given state x, but you actually have an evolution of the state, and this evolution of the state is subject to the actions that you are taking, right? So the u you compute at time 0. I'm representing both of these as vectors. So x itself could be a vector, x naught itself could be a vector, and then you have capital T or capital T plus 1 such states in your optimization problem. And for every time period, you also have to compute a control signal u0, ui, .ut that you want to apply to the system. And what you're trying to find is the optimal set of u control signals throughout the time period, right? And now your real complexity comes in because the actions you are taking are starting to affect the states you will observe in the future, right? So u naught affects x0 and u0 both affect what you observe at time x1 and so on, right? And if it's not a Markovian system, which means if it has memory, the future state evolution could be affected by anything in the past. If you have what is called a Markov decision problem, which means you have no conditioning on previous history given the current state, then also your future state x1 is dependent on x0, x2 is dependent on x1 and so on, as well as the previous control signal, right? And so computing this as a monolith, right, all the control signals throughout is very, very difficult, especially if you have stochasticity in the system. If your system is quite deterministic and well known, then you can do something like dynamic programming to figure out what the optimal control signals are at every time period. But if you have a lot of stochasticity, then whenever you take a certain decision, you could end up in a number of different states. And from that point, you have to compute your optimal control signals again. So unless everything is very small and tractable and you can run dynamic programming for every possible state that you will observe, only then can you actually rely on these kind of approaches. But most of the time, what you have to do is look at something like this, right? So where you forget about all of the previous steps and the fact that this is a huge sequential problem, and you only worry about the state you're observing at time t. Right? So you observe the state xt at time t. You think of an agent. I'm introducing this terminology now, and we'll kind of formalize it in a couple of slides. But you observe the state by this agent, and which computes some kind of action ut, right? And which is communicated back to the system. The system here being represented by the environment. So it accepts the action at time t ut and produces a new state xt plus 1, which is a function of a function g, say, or let's not call it g, it's confusing with the optimization parameters, but some function n of the previous state and the previous control action at the very least. And if it's not a Markovian system, then many previous states and actions as well, right? So the reason mapping xt to ut is quite a tough problem is because there is no need for this dynamical function f or any of these other constraints to be nice in the sense of being linear or convex and so on, right? So there are still classical control algorithms which can handle linear systems with quadratic cost. So these kind of things are well known and well solved, but in the real world, this is not necessary, right? So the f, g, and h could be quite complex. And so mapping the state that you observe to the action that you want to take can be very difficult, right? And for now, let's ignore the fact that previous states could also influence your future behavior and assume that the system is Markov, which means that xt is enough for you to decide what xt plus 1 will be. Right? You don't have to worry about xt minus 1, ut minus 1, and older states and actions. Right? But even with that, what we observe is that mapping this individual time step state to individual time step action is how most control algorithms will try to break down this problem, which is actually a monolithic optimization problem of all time steps taken together. And the methods we are going to talk about, reinforcement learning based methods, do this kind of mapping for a generic set of dynamics and constraints instead of focusing on specific forms such as linearity or convexity. So that's really going to be how this works. Okay, so if we look at industrial problems today, we see that there are two main kinds of contenders for control algorithms or for decision-making algorithms. The first and probably the most commonly used algorithms are heuristics or rule-based systems, which are essentially something that a human has defined, encoded, formalized, and coded into a program. So whenever a new problem, a problem by that I just mean a new state xt, is observed, these heuristics manipulate XT in a fixed way and produce a solution which has fixed decisions, at least up to the distribution, right? So you can also have stochastic heuristics which could take an action based on probability, but the distributions are fixed, they are hand-coded, right? So it's 50-50 this way or something like that. So you observe a new problem, you have existing heuristics that take care of it, you produce a fixed set of decisions, at least up to the distribution, and produce a solution. So this all depends on human knowledge and aggregated intelligence, right? So this path. Then you have meta heuristics, which are genetic algorithms or other evolutionary algorithms or neighborhood search kind of approaches, which given a new problem, say a new state XT, will start from scratch. They will have some kind of curiosity and exploration, which we will formalize in a couple of slides, but you can think of it as searching for a solution, right? So they'll do this online and they will produce a new solution. So this will be usually a very good solution, but it takes a lot of time to produce, right? And so that's something we want to avoid in a real-time control system. And so what we are trying to do is produce an AI-based approach which combines the good parts of both of these approaches. So you have human knowledge and aggregated intelligence from humans taken in the form of featureized or deciding what kind of signals are important, how do you modulate the incoming signals to produce good features and so on. You also have curiosity and exploration, so you're searching for good solutions, but you're not doing them when a new problem is posed. You're doing them during what is called training, right? So when you're computing the parameters of your control algorithm, that's when you do all your curiosity and exploration. So these are pre-trained offline algorithms, and the AI that goes into a real-world system is more or less a heuristic, but it's a heuristic which not been defined by a human. It's a heuristic that's been learned by an algorithm in the form of some mathematical parameters. Right. So for those of you who are familiar with neural networks, these could be the weights and biases of a neural network. So these are essentially a heuristic, right? It's a function that converts your input xt in some form to give you ut, right? So that's all it is. So I think of it as a heuristic, but you get a one-shot solution which is nevertheless adaptive to the data that you have observed. So based on the history that you have observed during training of all the states that you have seen, all the outcomes, actions, rewards, and so on, objective function evaluations, you hope that the parameters of this function f, which is taking xt as input and producing ut as output, have been optimized to produce good actions ut for a given state observation xt. So that's what we'll try to do. So at a high level, this is how it all works. So you have two key entities in any reinforcement learning algorithm, and most of you will have seen a diagram like this already. So I won't spend too long on it, except to point out that in the environment, which is an encapsulation of the behavior of the system or the plant that we are trying to control, we have an objective function which the plant is trying to maximize. We have a set of constraints consisting of both the dynamics of the system as well as the budgets that you have available for actuation and other things. And you could also have other actors, right? So it's not necessary that your system is operating in a silo or in a closed form. You could be interacting with other actors in the environment also. So if you take the case of autonomous driving, you have other cars on the road which you have to take care of. So these things have to be encapsulated in your environment, whether it's the real world or it's a simulation of the real world. The environment is expected to produce two things. We'll take the first one first, which is the state. The state of the environment is some kind of sufficient statistic that enables the agent to act on that state and produce a good action, right? So if the state does not have enough information, in essence, it's not a sufficient statistic, the agent will not learn to take good actions. And most people who do reinforcement learning for the first time, including myself, will make a mess of defining the states and actions, will not put in enough information in the state to actually take a good action, right? And so the way I've started to think about good state definitions is, if I were a person instead of this agent, which is essentially a computer program, if I were a person who was expected to take these actions, what information would I ask for from the environment before I was able to take this action, right? And that information should be present in the state that we are observing. Okay, so what goes on in the action is three things. The first and most important thing is it stores a previous experiences, right? So this is what is called a memory or a buffer, and you would be, you might ask why you need to store the experiences if you're training a policy already. The policy is essentially the mapping from XT to UT. And the reason is that sometimes your most recent observations may not be very reliable. And you will not know upfront whether they are reliable or not. So typically what people do is that they will store some amount of previous experience as well and put new memories into this experience buffer and train from the buffer rather than just train from the latest information, because otherwise you can get quite unstable behavior. The third thing that is present in the agent is curiosity. Curiosity in the sense of, even if you think you know what action is the best given the current state, you may not want to take that action all the time. So with some probability, you would try to take a random action just to see what happens, right? Which we tend to do a lot as kids, but not enough, I think, as adults. We tend to be quite greedy in our state to action mappings as adults, and it kind of takes away from the capacity for learning that we have. So curiosity is a set of random actions that you would try out sometimes, not necessarily in a deployed system, but at least definitely while you're training, right? And the thing that we have ignored so far is the aspect of the reward, which is the feedback that you get from the environment, given the state that you observed and the action that you took, what outcomes happened in the previous time step only, right? It's not taking care of the whole objective function. It's taking care of one time step worth of the objective function, if you want to think of it that way, one byte of the objective function, right? And the goal of the agent is to use these previous experiences, the power of curiosity, to train a policy that does this mapping well, such that you get that maximization, the argmax of F that we were trying to do from the outset, right? So observe the state, take an action that is maximizing the long-term reward. The long-term reward formalized in this way. So the total return, GT, which is another term or a name for long-term reward, is typically the thing that you try to maximize, and it is given by the reward that you get in the current time step, but also discounted versions of all future rewards. So gamma times RT plus 1, gamma squared times RT plus 2, and so on, where gamma is, of course, a constant between 0 and 1. Okay, and you can actually make it a closed set. So gamma can take the value 0, in which case you only care about the current steps reward, which is possible to do. This is a class of problems known as bandit problems. Or you could have gamma equal to 1, which is what happens when you have a finite episode and you're just trying to maximize the best possible final outcome. Right? So for example, if you're playing a game and your only outcome you care about is whether you won or lost, then you could just have a final term reward of 1, and everything else, all of these RTs are 0. Right? So in that case, you would put gamma equal to 1 and just care about the terminal reward. So this whole range of gammas gives you a control knob on how much you want to prefer future rewards to current ones. And that gives you a hold on how much long-term reward you want to optimize. Okay, and as you pass through this set of what is called an episode, which means a state at time t sent to an agent which produces an action, which is given to the environment, which produces a new state and a previous reward, and so on. So as you do this and you collect your experiences, you try to maximize the reward, the long-term return GT that you're trying to get. And the reason we are talking just from time step t onwards is because we are assuming that this is a Markov problem, right? So that we are assuming that all previous time steps don't matter, where you are now matters, and you just try to optimize from this point onwards. And in the programmatic sense, this is how it goes. So you have two classes in a way. So you have an environment class and you have an agent class. So in every time step, once you start the program, you get the state. You take an action based on the observed state and the policy you currently have inside the agent class. You communicate this state to the environment again as the next step action, which updates the step, creates a new state, and also gives you a reward feedback. And this goes on in a loop until you hit some kind of terminal condition. Either you are in a terminal state, such as the end of the game, or you run out of time steps, and then you train your agent to update the policy, which now gets shifted in here, right, for the next episode or game. So it's not necessary that you always do this in this order, but this is just one way of implementing it in the form of pseudo. Right, and there are many things you can do with this kind of approach. So one of the most famous recent papers is actually discovering how to do matrix multiplication faster using reinforcement learning. A lot of you might have already seen this, but the core idea is that when you do this kind of matrix multiplication, right, C equals A times B, even for this simple case of a 2 cross 2 matrix multiplying a 2 cross 2 matrix, what you can do is, instead of taking 8 multiplications, which you would do normally, right? So C1 would be given by A1, B1 plus A2, B3 and so on. So each term in the matrix is composed of 2 multiplications and 1 addition, which gives you 8 multiplications and 4 additions overall. You can reduce this, it turns out, if you define these 7 constants M1 through M7 in this way, and then each term is given by just adding these constants. Right? So you'll reduce the number of multiplications from 8 to 7. And so this concept can be extended to say, can you start discovering how these multipliers should be defined to minimize the number of multiplications you make, which has the potential to make large matrix multiplication much, much faster. Okay, and so people have done the same things that we looked at earlier, like this kind of approach, but for a matrix multiplication problem where your actions are defining these multipliers and your rewards are how quickly or in how few time steps can you actually build up this matrix, right? So there's a lot of things you can do with the basic concept of reinforcement learning. But today, for the last 20 minutes or so, I want to talk about specifically distributed industrial systems, which is what we promised at the start of this talk. Right? So the concept of this is as follows. If you think about your typical industrial closed loop system, right? So you have the system itself, which produces a large amount of data. Today, most systems will have some kind of SCADA or other sensors, IoT-based sensors, which will produce and measure a large amount of data. Right? So these sensors will produce a set of features, which even today in state of the art will go to some kind of machine learning AI-based algorithm, which forecasts what the system will do in the future, or it will produce some alerts in case some anomalies are observed and so on. The problem is that a huge dashboard or a huge amount of information is given to a human being to decide what needs to be done, right? So the forecast, alerts, and other data to actions mapping is done by a person. And this person, even though they have intuition and experience, which is invaluable and in many ways irreplaceable by AI, does get fatigued and they have cognitive limits, right? So this is not a good way to close a loop, in our opinion, because it creates fatigue and cognitive load on the person. So what we are trying to do is move the person up into a supervisory role and replace the person's day-to-day job by an RL or AI-based system. And so day-to-day, the RL loop is closing the entire closed loop control system, which means the entire thing is automated. You don't have to get involved on a day-to-day basis. But if something unusual happens, or if the person thinks something unusual will happen, which is based on their intuition and their domain experience, then they can intervene and change the actions that the system is taking, right? But most of the day, you don't want to get involved. And this kind of approach we have solved or used in many different problem areas. So one example is if you get empty ships coming into a port and you want to load them with containers as fast as possible, right? So how do you decide what is as fast as possible? Essentially, this is bottlenecked by the number of crane movements you have to do to pick up a container and put it on the ship. Okay, and the number of crane movements are significantly increased if you want containers from the bottom of a stack, right? So to get this container, you first have to pick up this container, put it away, and then pick up the next container and put it on the ship, right? So you want to decide some kind of optimal order that fills up the ship in the minimum number of container movements. And this is a problem that is very nicely suited to reinforcement learning. A, because it has very tight timelines. You can't really spend hours thinking about what the optimal sequence is. And B, because there are a lot of dynamics in the code, right? So you look at a snapshot of your yard at some point and you decide certain containers you want to pick up. But by the time you have put one or two containers away, some other crane has loaded some of these containers onto another ship. And your whole situation has now changed, right? So you can't spend another few hours now deciding on a new optimal sequence. So this is very well suited to a reinforcement learning problem. Similarly, we have worked with Indian Railways on the Konkan Railway line, right, which goes from Maharashtra all the way south to Kerala, on recovering from railway delays in this kind of scenario. Right, so the key constraint with Konkan Railway is that there is a single track running north to south in most places, so trains can only pass each other at stations. And so if one train gets delayed, everything else gets delayed. So recovering from this kind of state in the optimal number of moves, right? So which train should be held back? Where should two trains pass each other? Is it worthwhile letting this slow train leave the station, or should it wait and let a Rajdhani pass it? All these kind of decisions are again something that RL is able to take. Then there are problems in the airline industry where you have a large complex networks of connecting flights. And typically a large flight, if it is departing from say Bombay to Dubai, will be collecting a lot of passengers from other connecting flights, from Bangalore, from Chennai, from Pune, and so on. And so if one of these flights, say from Pune, is delayed, how do you decide whether you want to wait for that flight or whether it's more optimal to put those passengers on your next flight to Dubai, right? And so computing the optimal delay for a given flight is something that RL is able to do. And similarly, it's also able to do management of electric vehicle charging points, right? So which charging point should charge what amount of money to give you a certain amount of charge based on the time of day, the demand, etc. Right. So these are some of the flavors of problems that we have been looking at. But first, we'll come back to the problem that I promised to talk about again, which is how do you do lockdowns in a more quantitatively justifiable way, given all the things we have seen so far, the reinforcement learning approach and so on. And so the thing that we did was we put the disease model as we understood it into the environment. We also put in the network flow model into the environment. So left alone, right? Suppose you decide that nothing will be locked down. You can run a simulation where you see and predict what would happen to the disease overall in the country if you didn't have any lockdowns at all. Or if you completely lock down every district for all weeks, then what would happen, right? The two extreme cases. And what you're trying to find is some policy in between that gives you a balance between healthcare cost and economic cost. And so the way we did that was you have a district level RL agent, right, which is observing within the district how many new infections have been detected, right? So these would only be symptomatic patients, not asymptomatic, because it's not something you can observe. What is the network connectivity with other districts? How strictly are you enforcing the lockdown within the given district, right? And other such parameters. I think we had 8 feature inputs. From that, it would map to a simple binary decision, which is whether to lock the district for the next week or whether to unlock it for the next week. Okay, and you do this 700 times, given 700 different inputs of these types, and you get 700 different decisions for locking or unlocking various districts. And then you push them back into the environment model, you get certain outcomes in terms of healthcare costs, in terms of economic cost and so on. And obviously, these are at a very macro level. But you can do this, and you can try to then find, for a given set of assumptions about the disease and the network connectivity and so on, what is the optimal policy for closing or locking down a district. Okay, and we were able to show that we can actually do this fairly well. So first of all, we had to show that even a macro level simulator like this has reasonable predictions. Because if your simulator is really bad, there's nothing useful that will come out of training any policy on it. Right. So this was on the left a validation chart of what actually happened, which is in black and red. So these are two different public data sets that were available. And this goes from March 10th, 2020 up to April 19th, 2020. These were the number of active cases in the country. And this was the simulation seeded by, I think, 1 or 2 people who were infected on March 3rd, and for different random seeds as to where they were infected and so on. And from there, letting it progress, looking at the real decisions that India was taking, right? So the real decisions being a single day's lockdown on March 22, and then March 25 onwards, full lockdown, right? And so we were able to show that the model predicts pretty well what the data is going to look like, right? Without actually having any recourse to these red or black curves. They are just plotted for this thing, for comparison or validation sake. And so we said, okay, we have a reasonably good model which is able to match what is happening in reality with given the real policy decisions. Can we now train this model to actually do better than what actually happens, right? And so the caveat is, this is an academic exercise. I'm not saying that people should have done this because there wasn't enough time, or even budgets to actually look at this. So people were taking decisions by gut feel, and at the time that was the right thing to do. But if this happens again, maybe something like this could be useful. Okay, and the policy looks like this, right? The learned policies actually make sense if you plot them on some kind of sensitivity plot. Okay, so on this plot, on the x-axis, you have the fraction of asymptomatic people being tested in a node, right? So what is the positivity rate essentially within the node or the district? And what is the positivity rate in the country overall? Okay, and so the black points say, okay, you can leave this district open for the next week. All the red points say you need to lock down the district. And so it makes sense that if you have, 20% positivity rate in your district, but overall in the country, it's very, very small, just 2.5%, you can let the district be open because the chance of spread is quite low. The rest of the country is not facing issues. But similarly, if you have very low positivity rate in your district, but the country overall has very high positivity, say 25%, then you want to lock it down, right? So you can actually see what the model has learned and make sense of it. It's not just a black box model. So in the Konkan Railway case, which is another use case I talked about, the way we solved this was, you have to imagine that overall the railway line is very long, 60 stations or more than that. And what's happening, say, at the Mumbai end is not going to really affect what's happening at the Kerala end of the line, right? So there is, based on domain experience, a set of stations which actually affect what you should be doing, right? The trains nearby to you affect what you should be doing. And so we said for every train which is active in this network, let's look at a few stations in front and a few stations behind at the status of resources in each of these stations and the intermediate tracks, right? So the red, green, orange or yellow are essentially the states that you're looking at, just these few 9 numbers. And based on these 9 numbers and the priority of the current train, whether it's a Rajdhani or a passenger or a goods train and so on, you train a policy to minimize the overall delay in the network, given the mapping to just this halt or move decision. right? So if this train has completed its waiting time in the station, you call the train RL policy, look at the stations in front and the stations behind, and decide whether to move this train into the next resource or to hold it in the current resource. A very simple binary decision. And we were able to show that just doing this in a controlled way is able to potentially reduce delays by 20 to 30% overall, right? Compared to the state of the art, which is a human controller looking at a fixed state of stations, say 10 or 12 stations, and moving the trains within them. They can't really coordinate across different controllers and so on. And by the way, all of these are referenced by these papers that are being shared at the bottom of the slide. So if you're interested in what's happening there, feel free to go ahead and download them. The other use cases we have looked at is if you're looking at a controlled dynamical system, such as a robot. Right? This is a setup in our lab in Delhi, where you have parcels arriving on a conveyor belt in this direction. And the parcels, as you can see here, are of uncertain size before they come in. So you only know what the latest parcel coming up to you, the dimensions of that. And the robot has to decide where to put this parcel for onward shipment, right? So there are these 3 bins open over here, and over here. And you have to decide where to put the parcel, which of the bins, and within the bin, in what location and orientation. And your goal is to try and maximize the volume utilization of these bins. So we use RL to do this because it's a very time constrained optimization problem, and you don't have prior knowledge about the dimensions of the parcel. So it's a very nice problem to try and optimize using reinforcement learning. And so we were able to show that if you look at the current state and the potential future state of the bins after you have loaded the parcels and you put them through a convolutional neural network, you are able to predict what is the goodness, if you will, of a proposed location and orientation. So you can actually combine heuristics that shortlist certain locations which are probably good and ask the RL agent to decide which among them is best. Right? And so together these heuristics and reinforcement learning are able to maximize the capacity utilization. And finally, a couple of examples from the area of supply chain. So the first of these would be if you have e-commerce deliveries, right? Something like Amazon, where if you log into the website and look at a specific product, it will show you a deadline by which you have to book the product to get, say, next day delivery. And this deadline is decided based on the time steps, the processes that have to be carried out to bring that product to you, right? So if you are booking here right now, they say that you need about 2 hours in the warehouse to find that parcel, pack it, put the label on it and so on. 30 minutes to load it onto a truck and 3 hours for the truck to get to your doorstep. So overall, I need 5.5 hours to deliver it to you. So you have to book by a certain time, right? The delivery time minus 5.5 hours at most to get next day delivery. And our question was that if you want to reduce this time from 5.5 hours to 3.5 hours without further optimizing any of these processes, the 2 hours, half hour or 3 hours, which is something that is outside our control, what can you do? And what we said was, if we start to move parcels upfront, right, before the orders are even generated, then you might be able to do away with this 2-hour window because the parcels are already moving. And you just put a label on it when you launch an order or when you submit an order, and the truck immediately leaves for your doorstep, right? So this 2 hours is taken away with that. The question is, how do you know what is going to be ordered on a given day? Well, you have to use previous data to try and predict this, right? So if your match is coming up, India match is coming up, then India uniforms are likely to be ordered and so on. But obviously, you can't move everything that you predict is going to be ordered because that you don't have that much capacity. So the RL comes in to decide what is the best subset of products that should be moved upfront, right? So maybe there's a television which has a low probability of being ordered, but a high profit margin. So it takes precedence over, say, a few pencils, which you're sure will be ordered, 100% sure, but the profit margins are very low. Right? So all of this kind of combinatorial choices is being done by the RL algorithm. And this is actually something we have already tested with the UK-based very large retailer and shown that it works. Right. So similarly, we have done something for a European very large again grocery retailer where we say the store replenishment, the decisions for how much of each product should be delivered by a given store, how can we get that also trained by an RL agent. Then we can extend that concept from a single store to a multi-agent architecture where the warehouse and all the stores that it supplies operate together as independent RL agents, but sharing rewards and information in terms of state space with each other to take globally optimal decisions. So store one knows how much inventory the warehouse has and how much store 2 and 3 are likely to require, and so ask for replenishment accordingly. Right. So that kind of thing can now be enabled. And obviously, all of this supply chain work is subject to delays, all of those different time scales we looked at earlier. And so we have some more kind of theoretical proofs for how RL algorithms can be extended to take care of delays in your control system. And we have shown that observation delays and control delays or actuation delays in our case can be treated as equivalent if we extend the normal state space that an RL agent observes by the previous actions that it has already taken or rather computed but have not yet been implemented on the system, right? So if you extend your normal state into what we call an information state, then your RL agent actually has much better graceful degradation in this sense than normal RL algorithms have when you start increasing the delays in your system. And so again, this kind of concept we have used for making our supply chains more resilient and so on. And finally, I mean, it's not just serious industrial problems that we are looking at, but we have also tried out our hand at other NeurIPS competitions such as Bomberman, where you have a team of two taking on a team of other two agents and trying to kill them by placing bombs around them. Right? And so in one version, these two teammates can't even talk to each other at all. They just have to observe where the other agent is. In another version or another year of the competition, you could exchange one bit of information and so on. Right? And of course, there's partial observability. So you can't see the entire board. You have to hunt for your opponents and so on. So all of these coordinations, competing agents, coordinating agents, all of these things are kind of flavors of RL that we can use. So to summarize, what I would like to say is that real-time control of industrial operations can be thought of as a complex signal system that you are trying to modulate to your purposes. And the first key message is that we need to move away from AI as just being decision trees, regression, XGBoost, etc., and start thinking about what can AI do for automated decision making. And finally, the caveat to this is obviously AI is not intelligent in the sense that a human or even an animal is intelligent. It does not generalize very well. It is in essence just a function approximation, a nonlinear function approximation of very high expressive power, but nevertheless just a function, right? So y is equal to f of x is all that AI is right now. And so we need to kind of take care that we don't anthropomorphize what AI does. But as long as we take care of that, I think it is quite powerful as a control system. So that's all the material I had, but we're happy to take a few minutes of questions. I guess we're just about out of time. Yeah, go ahead. You don't need to raise a hand. I think you can just ask.
You once
Can I go ahead?
Flight plan where you use RL for the flight planning. You showed one example. So can you explain more about that? Like how you do it and what are the what is the agent
flight planning? This one?
Yes, sir.
So you want to know what a little bit more about the case study?
Yes, sir. Like what actions you take and what is the
Okay.
steps are there?
Right. So the system is as follows. For every aircraft, you have measurements of how many passengers are already available and how many future connecting flights are coming in for this aircraft. Right. So that have not yet arrived. And so if you have, say, reached departure time and you want to decide whether to delay this aircraft to wait for other connecting passengers or whether to release it, and if you want to wait, how long you want to wait, right? So the action is very simple in this case. It's a number that says I will wait for X number of minutes. Okay, and the states are really, like I said, the passengers who are available, the passengers who are coming in their expected times, and the context of this specific flight in the airline's network, right? So how many times so how many passengers from this flight will be connecting on future flights and so on. So if you are interested in this, there is a paper, a main track paper in AMAS, I think 2021, that talks about this by Arun Vasan as one of the authors. So you can take a deeper look at what they have done.
Okay, sir. Thank you.
So, I have a question.
Yeah.
Can you hear me?
Yes.
So, I think somewhere along your presentation, you talked about heuristics. And I also noticed that in the lockdown example, there was a nice structure to the policy. There was a boundary beyond which you lock down and below which you don't lock. So my question is that if you look at general reinforcement learning, we're supposed to learn this Qx comma A, an arbitrary function. Normally is very difficult to train that. So is there a way where you can bring to bear knowledge of policy structures onto this reinforcement learning?
Yeah, absolutely. So there are quite a lot of interesting papers coming up on representing policies, right? So the question you are asking is, I think, mainly about policy representation. The fact that arbitrary Q of S comma A as represented by a neural network could have any structure after training, right? And usually they are, overfitted, I would say. So you have too many parameters and not enough data. So the things that network learns can be quite difficult to decipher. But if you get structure onto this, there are ways of imposing structural constraints on a neural network, or even representing it with different functions such as Fourier transforms and so on. And there's a lot of interesting work happening on this kind of approach. So if you wish, I can kind of find the papers and send them to you. I don't think they are from TCS research, but they are quite well known.
Okay, thank you.
Yeah. Any other questions?
No, sir. One more. You have shown the actions as like only single action, either this or this. So what about the complexities when there are more than one actions we can take? And then that mapping and all.
No. So in the couple of examples that I mentioned, you just had binary actions, and those are simpler to train. But in this case, for example, your action is any arbitrary location and orientation in the bin, right? So that can be trained using algorithms. In this case, you have the quantity of each product that you want to produce. So it's a vector of continuous variables, right? So it's the quantity and for every product. So the number of products is the size of your vector and so on. So there's all sorts of algorithms that RL provides for handling different action outputs. In the case of this Powerman example, you have 5 or 6 different discrete actions. So you can move up, down, left, right, stay where you are, or place a bomb. So all of this is very naturally handled by current RL algorithms.
Okay. Thank you, sir.
Sure. Okay. I guess we are also out of time.
If there are no more questions, we can close the session for today. Thank you, Dr. Harshad, for an informative talk. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. Thank you and have a great evening.
Yeah, and there's a request to get the slides. So I can email them to you and you can share them, right?
Yeah, I can share them.
Yeah.
And it can be found in the web page.
Yeah.
The link to recorded video and the slides.
Okay. All right.
Thank you.
Thank you.